Hello, everyone. And my name is Zhang Qi, and it's my honor for me to have this opportunity to represent our team to share our solution to this year's WSDM Cup 2022, the Miracle Challenge. And we are from the Interactive Entertainment Group that is located in Guangzhou, China. And we are pleased to announce that our team won the second place in the surprise language track and the third place in the non-language track on the final leaderboard. And today my presentation is titled Enhancing Model Performance in Multilingual Information Retrieval with Comprehensive Data Engineering Techniques. And my presentation today, I will cover the following topics. And at first, I will introduce some basic information about the Miracle task and the data overview. And the second part about our details of the solution, which concludes the three stages, the retrieval, ranking, and the ReRanking. And the last part, I will share some experimental results and the summary. This is a general task introduction, and Miracle stands for the multilingual information retrieval across a continuum of languages. This challenge is designed to evaluate the effectiveness of the multilingual retrieval system in 18 different languages. And there are two tracks for the participants to compete in. The track one is for the no languages, and is provided with 4 training sites. And track 2 is a surprise language, which the training site didn't provide it. And this challenge is common in such scenarios where the goal is to retrieve relevant documents from a large corpus that match a given query. And the final evaluation is based on the NDCG at cutoff of 10. And this table presents basic descriptive statistics of the Miracle dataset, which covers 18 unique languages, divided into 4 parts: train, dev, test A, and test B. And each sample in the dataset includes a query, a passage, and a relevant judgment, including the relevance of the passage to the query. And this is a notable, we can see from the figure that there is a very notable difference across 18 languages. Therefore, we believe that transforming knowledge from the data-rich languages to those with limited data is crucial for achieving high performance in this task, especially for the surprise language track. And this is our whole framework for the solution. Our proposed solution revolves around the framework illustrated in the left side of the figure, which is composed of 3 stages: retrieval, ranking, and ReRanking. And in the retrieval stage, we utilize the pre-built indexes from the Pseudo-labeling and retrieve 1,000 documents per query per model, resulting in a total of 3,000 documents. And then we use the top 20 documents from the retrieval ensemble results for the ranking. And in the ranking stage, we build 3 different cross encoders to rank the documents retrieved from the last stage. And finally, we use an ensemble method to re-rank the model. Our retrieval work relies primarily on the Pseudo-labeling, which is very powerful and user-friendly toolkit for information retrieval. And we use Pseudo-labeling with 3 different types of indexes for retrieval, including a BM25 and 2 versions of the MDPR. And retrieval is performed in a zero-shot manner. And then we create an ensemble of these 3 retrieval results to produce a more robust one. And the top 200 candidates from the ensemble results are selected for the subsequent ranking. And this table primarily shows the top 200 recall rates for different languages in the training site, we can observe that the majority of the retrieval rates are about 0.98, and with two only exceptions for English and Indonesia. And we can therefore we can believe that the top 200 retrieved candidates for the ensemble result is sufficient for the next stage of the ranking. So we haven't do any new model building for the retrieval stage, just use the pre-built index from the passive learning. And this is our ranking framework. And the architecture of our ranking model is quite simple. We fine-tuned the model using the 3 different multilingual pre-trained language models, and RAMBERT, Info-X, LM, and MD-Beta. And the CLIS token embedding is utilized for the downstream task of binary classification. We first pre-fine-tune the ranking model using the MS Marco and Mr. Tidy datasets. Then we fine-tune it with numerical annotation data. Pre-fine-tuning significantly improves our ranking models, which implies us to explore more from the data aspects. Negative samples mining and two-stage augmentation techniques are further used to improve the model's performance. These techniques provide additional training data and helping the model to generate better and produce more accurate results. Additionally, to prevent overfitting, we also use the adversary training and the multi-sample dropout to improve the robustness of the model. After training, we feed the top 200 candidates from the retrieval stage into the ranking model to get a final result. And for the negative samples, as described in the Miracle paper, the Miracle dataset annotation is based on the top 10 candidates. So if we directly use the annotation data of the Miracle data for training, we are facing a selection bias problem. You can see the annotation sample space is just only a small subset of the entire retrieval sample space. And we all know that traditional machine learning assume that the training data and the test data are identically and independently distributed, using the annotation data directly from the ranking model. Sorry. If we're using the annotation data directly for ranking model training, it can result in a sample selection bias problem that negatively impacts the model's final performance. To avoid this issue, we add random negative samples from the entire retrieval space to the annotated data in order to align the two sample spaces. Our experimental results show that increasing number of negative samples leads to a smooth improvement in the model performance. This approach is much more efficient than using the negative samples from the entire document corpus. Given that the pre-fine-tuning greatly improves our ranking models, we believe that it is more important to explore the data aspect, and the query-to-query-to document approach involves linking the similar queries from the test site to those in the training site, using the selected training site queries and their associated annotation data for the data augmentation. We use pre-trained sentence transformers to calculate the similarity between the test and the training set queries. Then we multiply the similarity score by the annotated labels and the hyperparameter alpha to generate the final label for the augmented data. The alpha is used to control any potential noise introduced to avoid overfitting, and it is set to 0.9 in most of our experiments. In addition to Q2D, we also use pseudo-labeling as a method of data augmentation. This involves generating pseudo-labels from the test site using our trained models. By doing so, we can increase the amount of the data used for training and improve the model's adaptation to test site queries and documents. In our experiments, we found that the soft label outperforms the hard label, as the latter may increase the risk of overfitting. To maintain the quality of the training data, we randomly select a portion of the pseudo-label data and multiply the soft label by 0.9 to produce the final label used for training. This technique significantly improves our models. And finally, we use the model ensemble to further improve the ranking results as achieved 0.008 improvement on the public leaderboard. Our base models for ensemble include ReRanking, Info, XLM, and MD-Beta, each trained with different settings to generate diverse predictions. We determine the weights for the averaging of the prediction of each model, primarily based on their scores on the public leaderboard. Since the Info XLM model performs the best, we give it a higher weight. This table presents the overall results of our experiments. Our solutions are consistent across both the non-language tracks and the surprise language track. In the retrieval stage, we achieved a score of 0.635 using a hybrid result of the BM25 and the MDPR from the Passerini. And for the ranking stage, we started with MD-Beta as our baseline model. The score of the pure MD-Beta model without any tuning was 0.701. And next, we conducted 3 lines of experiments using different data engineering techniques and based on different pre-trained language models. Finally, we used the best models from each line of the experiments to create the final ensemble. This figure displays the results of our experiment from the previous slide. Based on the hybrid retrieval result, we were able to achieve a score of 0.701 on the leaderboard with the MD-Beta baseline ranker. And we conducted 3 different lines of experiments starting from the baseline using different pre-trained language models and the data engineering techniques. All the models were pre-fine-tuned using the MS Marco dataset, which has been proven to be particularly effective. And the MD-Beta and the ReRanking experiment lines show that the pseudo-labeling brings a significant improvement of approximately 0.03 to the score. Further fine-tuning with Mr. Tidy also helps to improve the score by 0.05. However, this improvement is not as substantial as we had hoped. And the Q2D brings about 0.01 improvement. Towards the end of the competition, and we discovered that the sample selection bias that was hindering the model performance. To address this, we added random negative samples from the top 200 ensemble retrieval results in the training site that were not annotated as positive. As shown in the Info XLM experiment line, the yellow line on the graph, and we can see that the score increases from 0.764 to 0.802 as the number of negative samples increases from 5 to 200. We found that using 100 negative samples is a good trade-off, as the improvement is much more pronounced when increasing the number of the negative samples from 5 to 100 than from 100 to 200. Finally, with a simple ensemble, we were able to achieve the final score. And in summary, Our solution consists of three main components: retrieval, ranking, and ReRanking. Our focus is on the ranking stage, and we improve our ranking model using comprehensive data engineering techniques step by step. We started our experiments with multilingual cross-encoder models. To further enhance the model's performance, we fine-tune the ranking model with more relevant data, such as MS Marco, Mr. Teddy. As fine-tuning with more data results in substantial improvement, we believe that data augmentation would also be beneficial. The rest of the pseudo-label and Q2Q2D techniques further improve the model performance. To address the issue of the sample selection bias, we incorporate the random negative samples to align the sample spaces of retrieval and ranking. And finally, we use model ensemble to get the final results. That's all. Thank you for your attention. And we would like to express our gratitude to the Miracle Organizing team. They really contribute and paid a lot of efforts through this whole competition. And we would like to thank everyone involved in organizing this and sponsoring this WSDM Cup 2023. Thank you.